Hello, I'm John Holdren, professor at Harvard University's Kennedy School of Government, and the lecture today, An Introduction to the Energy Climate Challenge, is the first lecture in a series of 10 addressing that enormous challenge. The organization is that there will be 10 one-hour sessions. We'll do our best to provide essential information about global climate change, about the dominant role of society's fossil fuel-dominated energy system in causing global climate change, and the technical and policy options for addressing it, with emphasis on the roles of China and the United States. The lectures, which are by Harvard University experts who have worked closely with Chinese colleagues on these topics for many years, will present key insights from the fields of climate change science, energy system studies, environmental and resource economics, and policy analysis, and will draw on the most recent findings from relevant national and international studies. The speakers in the series are listed here: Professor Joseph Aldi, Professor Akash Deep, myself, Professor Henry Lee, and Professor Daniel Schrag. In this first session, we will cover the points indicated here, starting with 5 key findings from climate change science, looking at climate processes and the role of greenhouse gases, looking at society's energy system as the biggest climate disruptor, looking at the indicators of human disruption of climate up until now, looking at the harm being caused by climate change to human well-being until now, and finally an outline of the topics that will be covered in the remaining 9 sessions. So let me start with 5 key findings from climate change science. Science has established beyond any reasonable doubt, first, that Earth's climate has been changing for many decades in ways that are not explainable by natural influences. Second, the main reason for those changes in climate is the emissions of heat-trapping gases from our energy system and secondarily from land use change. Third, human-caused climate change is already causing harm to human health, property, economies, and ecosystems. Fourth, inevitably, the problem will get worse in the future because of time lags in the climate system and in designing and implementing society's responses. And finally, and very importantly, the future harm will be much smaller if society quickly ramps up its remedial efforts than if it does not. Let's turn now to climate processes and the role of greenhouse gases. Earth's temperature depends on the balance between incoming and outgoing energy. Greenhouse gases, abbreviated GHG, in the atmosphere influence this balance. Some greenhouse gases exist in the atmosphere naturally, and some are added by human activities. The most important naturally occurring greenhouse gases are water vapor and carbon dioxide. Without them, the surface of the Earth would be too cold to support life as we know it. But when humans burn coal, oil, and natural gas, the so-called fossil fuels, or wood, the combustion products, mostly carbon dioxide and water, go into the atmosphere. Biomass burning and other land use change also emit carbon dioxide and water. The water remains in the atmosphere only briefly and adds little to the natural water vapor already there. But much of the carbon dioxide added by humans remains for decades to millennia, so its concentration in the atmosphere builds up over time. This picture of measured carbon dioxide concentrations from the Mauna Loa Observatory in Hawaii is the July 2024 update of the most famous graph in all of climate science. The measurements from the top of Mauna Loa, 4,205 meters in elevation, constitute the longest continuous direct measurement of carbon dioxide in the atmosphere. Concentrations of methane and nitrous oxide, CH4 and N2O, are the second and third most important greenhouse gases after carbon dioxide that are being added by human activities to the atmosphere. These graphs show the increases in recent decades of both methane and nitrous oxide. Now let's turn to society's energy system, which is, as we will see, the biggest climate disruptor. This graph shows the human emissions of heat-trapping gases, greenhouse gases, that are causing the buildup of the concentrations of these compounds in the atmosphere. And what you can deduce from this graphic, the fine print is a little hard to read, but it shows carbon dioxide from fossil fuels, it shows carbon dioxide from net deforestation, it shows methane, it shows nitrous oxide. And what one sees if one reads carefully is that energy supply and use are responsible altogether for about 2/3 of the total emissions of heat-trapping gases. What caused this? The growth of population and prosperity from 1850 to the present increased world use of energy by over 20-fold. Almost all of that increase came from burning fossil fuel, coal, oil, and natural gas, as this diagram very clearly shows. In 2022, last year, coal, oil, and natural gas still supplied about 80% of world energy use and 61% of electricity generation. Carbon dioxide emissions from fossil fuel burning came to dominate the emissions from land use change after 1950, as shown here. Land use change emits carbon dioxide when previously living vegetation is burned and when cultivation speeds up decomposition of soil organic matter. This chart shows world, China, US, and India population, gross domestic product, energy, the fossil energy share, and the emissions of fossil carbon dioxide in gigatons, billions of tons of carbon dioxide in 2022. And what one sees here very conspicuously, and by the way, these figures include estimates of traditional biofuels use, that is, fuel wood, charcoal, crop waste, and dung. Many tabulations do not, but we do. What you see very clearly here is that China has become the world's largest emitter. It has 79% of its primary energy coming from fossil fuels. Its emissions are twice those of the United States, although it must be added that historically, the cumulative additions of carbon dioxide to the atmosphere from the United States are the largest. But China is currently the largest year-by-year emitter. It also shows that in purchasing power parity terms, China's gross domestic product has already passed that of the United States. Looking at the electricity component, one needs to note that about 40% of total energy supply is used around the world to generate electricity. And here one sees the total net electricity generation. Net means you don't count the internal electricity use of the power plants themselves. One talks only about the amount of electricity exported for human use. Again, one sees China has passed the United States by far in total electricity generation. Then you see the fossil shares, the hydropower shares, the share from other renewables, particularly wind and solar photovoltaics, and the share from nuclear. And again, the striking number is that in spite of how much we all hear about the renewable energy sources and about nuclear energy, fossil fuels, the fuels that are releasing carbon dioxide to the atmosphere and directly driving climate change, are the biggest source of electricity generation, as well as the biggest source of energy use as a whole. Let's look at indicators of human disruption of climate up until now. And this chart shows global warming during the thermometer era. What the thermometer era means is the period of time over history during which measurements, direct measurements of warming worldwide over the land and over the ocean using thermometers became sufficiently widespread to warrant calculating a global average surface temperature. And that's what's shown here, the global average surface temperature of the Earth, including both land surface and ocean surface. And the result, of course, is very striking. First of all, the last 9 years have been the 9 hottest years on record. And on the upper left, they're listed there in the order of the hottest years. And by the way, it looks like 2023 is on track to set a new record, exceeding 2020 and 2016. And a very key point is that from 1750 to 1900, natural cooling and human-caused warming were in rough balance. So globally and annually, the average temperature stayed roughly constant over that period of 1750 to 1900. But the 20th century, as one sees here, saw global warming because the human influence had become dominant over the natural influences. Very important to understand that the complexity of the climate system makes warming uneven over the surface of the Earth. Uneven temperature changes, as indicated here, mean that atmospheric and ocean circulation change in both hemispheres. You get rapid loss of sea ice in the far north. You get thawing of permafrost in the far north. And you get other extreme impacts in the far north, which as a whole is warming 3 to 4 times faster than the global average. Another very important point is that the extremes of temperature and other climate-related variables increase faster than the averages increase. And the reason why is shown here. In a moderately warmer climate, that is moving the distribution of temperature a little bit to the right from the average, leads to very large increases in the extremes, very large reductions in the frequency of extreme cold spells, and very large increases in the frequency of hot spells. And one sees that in the circumstance that all-time high temperature records are being broken everywhere. You see a number of examples here. With a bigger chart, we could have listed 100 of them, where all around the world, the highest temperatures ever recorded have been recorded in the last few years. It's true for China, India, the United States, South Africa, Siberia even, reaching a temperature of 38 degrees Celsius in June of 2020. Absolutely unheard of. But it's very important to emphasize that these changes are not just about temperature. Climate means weather patterns, the averages, the extremes, the timing, and the spatial distribution of not only hot and cold, but also of cloudy and clear, of humid and dry, of drizzles, downpours, and hail, of snowfall, snowpack, and snow melt, of breezes, blizzards, tornadoes, and typhoons. And the point is that climate change entails disruption of those patterns. Global average temperature, which climate scientists love to talk about, is really just an index of the state of the global climate system as expressed in these patterns. And small changes in that index, global average surface temperature, correspond to big changes in the system. It's much like your body temperature, where a change of 2 degrees Celsius would be telling you that something is seriously wrong with your body system. Similarly, a change of 2 degrees Celsius in global average surface temperature will be telling us that something is seriously wrong in the global climate system. And those changes matter. They matter because climate governs, and therefore altering climate affects the availability of water, the productivity of farms, forests, and fisheries, the prevalence of oppressive heat and humidity, the formation and dispersion of air pollutants, the geography of disease, what diseases exist and propagate with what intensity in what geographic regions, the damages from storms, floods, droughts, and wildfires, the property losses from sea level rise, the expenditures that society must make on engineered environments to try to compensate for changes in the climate, and last but not least, on the distribution and abundance of species, the species we need, the species we love, and the species we hate. This graph shows the acceleration of sea level rise over recent decades. The sources of sea level rise are the shrinkage of glaciers and the great ice sheets on Greenland and in Antarctica, thermal expansion, the ocean increases in volume when it gets warmer, and groundwater mining, where all around the world we are pumping groundwater for human use more rapidly than it is naturally recharged, and that too is contributing to sea level rise. And the crucial point here is that the rate of sea level rise continues to go up. This diagram shows the geographic extent of Arctic sea ice at its annual September minimum. The graph shows from 1978, when satellite imagery first got good enough to determine the area covered by sea ice, and 2022. Shrinkage in the area of the sea ice at this moment of annual minimum has been basically 50% over this period. The area has gone down by half. And shrinkage in the average thickness has gone down by 3/4, by 75%. And that shrinkage in thickness means that future reduction in area is going to be even faster than what we have observed so far. Now, it's important to emphasize that sea ice floats, and so when it shrinks, that does not affect sea level. But the change from ice to open water, while it opens economic opportunities, has drastic effects on regional and hemispheric temperature, winds, storm impacts, and on valued species. Ocean acidification, another impact of the addition of carbon dioxide to the atmosphere. The ocean takes up part of the excess carbon dioxide in the atmosphere, and that leads to a chemical reaction of the carbon dioxide and seawater that produces the weak acid carbonic acid, H2CO3, and that lowers the pH of the ocean. That means it increases the acidity of the ocean. And that increased acidity affects the distribution and fitness of marine creatures that make their shells or their skeletons from calcium carbonate. That includes corals, shrimp, oysters, and some of the zooplankton that sit near the bottom of marine food webs. Let's turn to climate change harm to human well-being up until now. Key point: significant damage is already happening. Climate change is not just a problem for our grandchildren and great-grandchildren. It is increasingly a problem for everyone alive today. At a mere 1.2 degrees Celsius above the 1880 to 1990 global average temperature, which is where we are now, the world is already experiencing significant increases in big wildfires, in long droughts, in powerful storms, in deadly heat waves, in torrential downpours and flooding, in permafrost thawing and subsidence, in the range and virulence of pests and pathogens, in the degradation of marine and terrestrial ecosystems, in coastal erosion and destruction from sea level rise, and in impacts on the distribution and abundance of valued species. All of these changes are plausibly linked to climate change by theory, by models, and by what climate scientists call fingerprints, that is, the patterns in space and time with which the increases in these destructive phenomena are occurring. On all of these issues, virtually all of the new news from climate science over the last several years has been bad news. Virtually everything is getting worse more rapidly than was predicted by science only 10 years ago. The sad fact is that the goal of the UN Framework Convention on Climate Change, which was agreed in Rio in 1992, which was to avoid dangerous human interference in climate change, that goal is now history. It's done. We are already experiencing dangerous human interference in the climate system. We see this in the recorded, documented reality that many types of weather disasters are increasing. This shows the pattern over the last several decades in floods, mudslides, extreme temperatures, droughts, and so on. And you see around the world, the extreme events are going up very dramatically. We're seeing more flooding resulting from bigger downpours. The physics of this is relatively simple. A warmer atmosphere holds more water, and that means more water can and does come down at one time. Slower moving storm systems, another consequence of climate change, is further increasing the downpours. We are now seeing so-called 100-year floods. Floods were only expected to occur once in 100 years, now occurring once in a decade or even more in many places. We saw 3 500-year floods occurring in Houston, Texas, in the United States over a period of just 3 years. The United States, China, Europe, India, Japan, Africa, Australia have all been hard hit by extreme flooding in the period from 2018 to 2022. The pictures at the top on the right, an example of extreme flooding in China in August of 2023. At the bottom, extreme flooding in Washington, D.C., the United States capital, in July of 2019. Wildfires are getting worse. This is a picture for the United States, but it could be replicated over much of the part of the world that is vulnerable to wildfires. The incidence of wildfires, with of course some year-to-year variability, the incidence is going up. Contributing factors to that are higher heat, more drought, higher wind, more dead trees as a result of climate change, and more lightning in a warming world. The linear trend in black shows that the burned area in the United States per year, the annual burned area, increased 4.5 times over the period shown from 1983 to 2022. Worsening drought. Again, multiple causes of worsening drought from climate change. Higher temperature means bigger losses of water from the soil to evaporation. More of the rain falls in extreme events as a result of climate change. That means more of the water is lost to flood runoff and does not end up in the soil. We're seeing more rain and less snow in the mountains, which means more runoff in winter, meaning less runoff in the summer when drought becomes a problem. We're seeing earlier spring snowmelt, which also means less runoff for the summer, and altered atmospheric circulation patterns resulting from climate change are also playing a role. And one sees in the picture on the right the very depressing, record-breaking drought in China last year, 2022. Tropical cyclones have been getting worse. Tropical cyclones are called hurricanes in the Atlantic and Eastern Pacific. They're called typhoons everywhere else. And you see that the strongest, largest tropical cyclones, whether hurricanes or typhoons, have occurred in virtually every basin of the ocean that is susceptible to these cyclones. The worst ones have occurred over the last decade or so. One sees on the top the superstorm Sandy in the eastern United States. On the bottom, you see Winston in Australia, one of the strongest typhoons ever to occur in the South Pacific. Here one sees the record of high tide flooding resulting from rising sea level. These particular illustrations are for the United States, showing over a period of decades the very sharp increase in urban flooding during high tides. But this problem is occurring in many parts of the world, including in coastal China. Coral bleaching worldwide is proceeding apace. That is due to warming, acidification, and other stresses on the corals, all combined. We've seen large bleaching events in the Pacific in 2019 to 2023, threatening reefs all around the Pacific Ocean. And it's worth noting that coral reefs are the second largest reservoir of biodiversity on the planet after tropical forests. And by the way, tropical forests are also threatened by climate change. Many of these changes can harm or are already harming human health. And this diagram from the Centers for Disease Control and Prevention in the United States simply shows all of the many ways in which climate change can damage human health. In red at the upper left, heat-related illness and disease and cardiovascular failure from those syndromes have received the most attention historically, but all of the other factors are also important, and recent evidence has documented climate-linked worsening in most of these categories. The wet bulb globe temperature is a measure that correlates with the loss of capacity to do work and with the risk of heat stroke, often leading to death. It's a measure that combines temperature, humidity, wind, direct solar exposure, and other factors. This diagram shows the wet bulb globe temperatures experienced in the decades from 1990 to 2009 around the world. And what I'm going to show you in a minute is that this is getting worse and will continue to get worse. It puts at risk, in the warmest parts of the world, the capacity of people to do heavy work outside in agriculture and forestry and fisheries and construction, to do such work without risking their health. This shows one of the many diseases that's affected by climate change, dengue fever. Vectorial capacity combines the area and the intensity with which this particular pathogen multiplies and infects people. It is among the several vector-borne diseases that are becoming more widespread and more infective as a result of climate change. So let me turn finally to the coverage of the remaining sessions, the 9 more topics. First, the rest of Unit 1, the introduction. We'll look next time at what's ahead for energy and climate change. Then we'll look at the introduction, an introduction to the policy options and the associated economic and political challenges. Then we'll start Unit 2, deep dives on technology, policy, and economics, looking in Session 4 at electricity and the challenges of the climate transition. In Session 5 at carbon capture, utilization, and storage, direct air capture, and geoengineering. In Session 6 at energy efficiency and transportation, industry, and buildings. In Session 7 at land use, agriculture, and forestry. In Session 8 at adaptation to heat waves, droughts, and sea level rise. And then finally in Unit 3, covering international dimensions and synthesis, a session on international dimensions of climate policy and a synthesis pulling it all together. A few resources for Session 1, some of the main studies on which the findings I've reported here are reported. And finally, a thank you for your attention.